whatever, manufacturing, everywhere, AI/ML is there. All these sophisticated systems have been driving lately, uh, invariably every application, right? So let's say we have built an AI system to detect fraudulent transactions. So millions of transactions, UPI transactions happen all over the country. On a daily basis, millions of transactions happen. You developed an AI system for detecting whether a particular transaction is fraudulent. Okay, let's say this is what is happening. Somebody somewhere, some remote corner in India has a coffee and pays the bill using the UPI app. Okay, the transaction is fed to an AI algorithm. Okay, now your objective is to classify whether this transaction is fraudulent or genuine. Okay, so this is the system you built. The magic is in that AI algorithm box. Okay, that AI algorithm can be anything. During the course of the summer school, I'm sure you will learn a lot of AI algorithms, starting from a very simple logistic regression, linear regression, all the way to maybe vision transformers, even more sophisticated like diffusion models, etc., GANs, etc. So let's say it's a simple neural network, multi-layered perceptron. And I'm not going into how you trained and all that. Let's say you already have developed it. And one of the transactions you are analyzing is somebody paid 10,000 rupees at a coffee shop. To complicate a little bit, let's say it happened at 3 a.m. on some day. Okay. Now my question is, do you think it is fraudulent transaction? Somebody paid 10,000 rupees in a coffee shop at 3 a.m. How many think it is fraudulent?
Yeah, it's likely to be fraudulent.
Good. Somebody thinks it is likely, more likely to be fraudulent. Anybody? Right. How many think it is not a fraudulent transaction? It is not likely to be a fraudulent transaction. How many think that way? Sorry. Okay, that means all of you think it is a fraudulent transaction. Why so?
Because it is at an unusual time, relatively unusual, and also the amount is so big. People don't usually pay that much at a coffee shop.
Excellent, excellent. That's one explanation. I completely agree with this explanation, because typically you don't see 10,000 rupees in a coffee shop as a bill. Also, 3 a.m., it is very, very unlikely that somebody will pay in a coffee shop, right? 10,000 rupees. But then there are exceptions. Let's say it's a Friday night or Saturday night, people are, partying or something in urban environments, let's say in metros like Mumbai, Bengaluru, Hyderabad. The nightlife is active even at wee hours like 3 a.m., 2 a.m. Also, some posh shops, there may be some shops when you go with a team of, let's say, 5 people, 6 people, they may charge you on the range of 10,000 and all. And there are some shops that charge you 10,000. It's not like it is impossible, right? So whatever is the decision, whatever is your inference, you need to have an explanation why you believe that this particular transaction is fraudulent or not fraudulent, right? That way, it is more agreeable system in practice, rather than just spitting out the inference and not answering the question why. We don't want such a system, right? We want a system that accurately predicts what that transaction is going to be, and also why it believes the transaction is fraudulent or not fraudulent. Okay. Now, the whole point of explainability in AI is this question: can the model help us understand why it said what it said? Okay, we don't stop at what it says. Okay, it is important what it says, whether it is fraudulent or not fraudulent, but we don't stop there. Okay, we want to understand why the model said what it said. Okay, all AI models that are driving very critical applications are sophisticated, no doubt about their sophistication. The data they consumed to get the intelligence, the compute invested in getting these models trained, and the intelligence went into the AI ML engineers, scientists that sat together and brainstormed to come up with this kind of a model. No doubt about it. All models are sophisticated, but sometimes the designers themselves do not fully understand some of these behaviors. Okay, so that is the problem. Often the case, these models are treated as black boxes. It takes input, it gives output, but we don't really understand them completely. Okay, I'm talking about even the developers who designed and developed them. Okay, even them, it is not very clear. Okay, so that is where explainability in AI comes into picture. What is explainable AI? It is a collection of techniques and tools that can help us understand how the particular AI/ML model produces the inference that it produces. Okay, whatever is the inference, it can be any system, it can be a classifier, it can be a regressor, it can be a generative model, whatever it is. These set of tools and techniques help us understand how that particular model produces what it produces. Okay, that is called explainable AI. Okay, so we all know data science takes a lot of data and gives us models. Okay, models are technology. You use them to drive some applications, but then behind them there is a knowledge, right? So we want the knowledge. Okay, why this particular transaction is fraudulent or classified as not fraudulent? Why this particular MRI, upon detecting or analyzing by a particular AI, it is predicted as a presence of a tumor is detected, or not a presence of tumor is detected. All that is fine, but we want that knowledge. Why? Okay, so the data sets, upon consuming the AIML models, upon looking at lot of data, the model is being created, but the model is only a science. Okay, we want that knowledge. Okay, why? What I mean by knowledge, for example, let's say you designed a model, a simple model that measures certain healthcare data, for example, that takes in the BP, the sugar levels, and the age, gender, uh, the lifestyle habits, and predicts whether the person is susceptible to get a heart attack in next 6 months or not. Let's say you designed this model. Okay, you collected a lot of data from patients and healthy people and all that. You created a wonderful model which is almost 100% accurate. All that is fine. The data science part is done. But what is the knowledge? When do people suffer heart attack? Can you answer that question? No. Without understanding the model, without understanding its inference, the knowledge is not there. Let's say if the model is explaining, because the patient, one particular patient was predicted to be prone to heart attack. Then you ask why? Why do you say that? If at all there is an explanation saying, see, this person is an alcoholic, he doesn't exercise much, and all that makes him susceptible. That is the knowledge. Where does it come from? Not the black box model itself. Provided there is an explanation, you don't access this knowledge, right? You stop at only science. But knowledge is important because you want to understand why the model predicted what it predicted. Okay, that is where explainable AI comes in picture, converting the science to knowledge. Okay, now let's talk about where and all this explainability come into picture. Okay, let's say again you designed a simple binary classifier which is taking images of dogs and wolves, and classifies it either as a dog or a wolf. Okay, so particularly there is Siberian Husky, a category of dog breed which looks very similar to wolves. Okay, so it's a supervised learning. You have collected lot of data, labeled them either as dog, which is Siberian Husky breed, or a wolf. Okay, now let's say you have thousands of such images. You went on training a convolutional neural network, which is one of the coolest models for performing image recognition, object classification tasks. Okay, the model is performing very well, close to 100% accuracy. It's all good. But now you want to understand how well the model is performing. Okay, you take the model, you give this input, and it predicts a Siberian Husky, which is correct. The ground truth label is also Siberian Husky. Now you want to understand the model. What or why the model thinks it is a Siberian Husky? Let's say there is an explanation algorithm which provides this as an explanation. What is the explanation? It is highlighting the parts of the input because of which the model thinks it is a Siberian Husky. Now, my question to you is, look at the explanation, which is the parts highlighted in the input as the reason for the prediction. So, do you think this is a good explanation, or do you think the model is doing good job of classifying? How many think so?
So the question is not clear. Can you please repeat?
Okay, so the classifier predicted input to belong to Siberian Husky category. Then you asked the classifier why it believes the input is a Siberian Husky. Then, as an explanation, the model gave away these regions. Okay, whatever is not blurred, whatever is not removed in the explanation is the reason. The model says because of the presence of these content, these objects in the input, it believes the input is a Siberian Husky. Look at the regions. What is highlighted as the reason behind the prediction?
The middle picture, model understanding.
Correct. The middle picture. Yes, that is. That is the explanation by the model. Model highlights these regions. Because of these regions, it believes the input is a Siberian Husky. Are you happy with this explanation? Are you happy with the model?
No, not.
No,
No,
it's
sir.
not clear.
Why not?
It does not make sense to us.
Why doesn't it make sense? Because it sees snow and some, it's a dry vegetation, I think. So don't you think it is a correct explanation for why the input belongs to Siberian Husky?
But it didn't guess the dog properly, the husky.
Right. See, in order to say this is a Siberian Husky, it has to identify the characteristic features of that Siberian Husky, right? But instead, what the model looks and highlights is the snow, presence of snow. See, presence of snow is not a characteristic of a Siberian Husky. It has a, different, fur. Because of that, it can say. But a presence of snow in the image, or because there is a snow in the image, the model thinks it is a Siberian Husky. It's not convincing. You don't want to buy such a model because it is a spurious correlation present in the input and the label. Maybe it happened that all of the Siberian Husky images had snow present in them, and it understood, the model incorrectly understood that, okay, whenever there is snow, it is labeled as Siberian Husky. It is a wrong way to learn, right? It should otherwise look at the characteristic features of the category, what makes a Siberian Husky what it is. Then it should highlight those regions, right? This particular model is almost useless because it didn't learn anything about the Siberian Husky category. It just caught some spurious correlation that is present in the input images. Okay, so it is a bug. How did we find out? Because we asked an explanation. If you don't ask an explanation, you feel it is doing 100% accurately on the validation set, and you will be happy. But you will be ignorant of the such a big bug. Okay, so the explanations will help us find if there are any bugs in the model. Okay, now how do you go about correcting the model? Now you understood the model is not learning properly. It is only looking at the snow and thinks. Sorry. Maybe somebody unmuted. Okay. So now the question is, how do you go and correct?
Excuse me. So I
Yes,
had
please.
raised hand.
Yes, please go ahead.
I just wanted to know how it's a digression maybe.
That's
This
okay.
how do we ask the model how it understood? I mean, how did we dig out this part that
Right.
this is how it distinguished? between
Excellent.
Siberian Husky.
Right, right. That we will discuss in the second part. Okay, I am motivating you to understand why it is important to ask explanations. How I'll cover in the second half of the lecture. Okay.
All right, thank you.
All right, that's a good question. I didn't reveal that how I got this explanation. There is a whole lot of literature how you can ask the model for explanation. Okay, but for the first half an hour or so, I'll try to motivate you and convince you that explainability is badly needed. Okay, so one thing why it is needed, because you can verify the model and understand if there are any bugs in its learning. Okay, now in short,
Sir,
yes, please.
sir, what is the difference between interpretation and explainability?
Okay, I'll come to that also. One of the slides exactly have that differentiation. It's good.
Okay,
It's good. Yeah, yeah. It's good that yeah. I have that exact slide. Okay, right.
okay.
Just please bear with me for another 5-10 minutes. Okay, right. So in short, the explainable AI facilitates model debugging. Okay. Now let's look at another case. See, nowadays AI is used in all sort of critical applications. So one such application is processing the parole applications of inmates. Okay, in the US and other countries, the judges, while processing the applications of inmates for parole and early release, they take help from AI. They feed all the data of that inmate and ask the predictive model whether it is risky to release this defendant. Let's say one such case, the model said it is risky to release. And you don't just buy it, okay? The judge will ask why. Can you explain why you say this defendant is risky to release? Then let's say it comes out with a model explanation because of the race, because of the gender. Also, the length of the bar indicates the weight assigned by the model to these features. Okay, because of the race, because of the gender, because of the crimes, the algorithm, the AI algorithm thinks it is risky to release. Now, again, the same question. Do you think this model is doing good job?
No, sir.
Why not?
So it is simply making an assumption based on the race of the person.
Right. Go
Yeah,
on. Go on.
it is not giving you weightage to crimes.
Yes. Excellent. See, when do we say what is a reasonable thing to say whether the person is risky to release? You look at the nature of the crimes, you look at the frequency of the crimes, not the race, not the gender, right? The algorithm should not focus more on those features. Instead, it should focus more on the nature of the crime, severity of the crimes, frequency of the crimes. All that should be considered strongly. But instead, this algorithm is looking at what race the person belongs to, what gender the person belongs to. It is discriminating based on these factors, right? So this algorithm is biased. You don't want such an algorithm to take critical decisions. That is why you need an explanation for these algorithms. Okay, in short, it facilitates bias detection. Okay, now let's look at another application. These days, banks are also using AI algorithms to process the loan applications. They'll use AI to decide whether it is risky to sanction the loan or not risky to sanction the loan. Let's say you applied and one of the model denied the loan. Obviously, the management would like to ask, or the customer would like to ask, what makes the AI algorithm think it is risky for the bank to sanction the loan? Okay, and not only that, the bank as a friendly business, they would like to suggest the customers, the applicant, see, because of these reasons we have to deny your loan, and there is a way for you to enhance your application. How? Let's say it comes up with a suggestion. You're falling short of the annual income. Why don't you seek a rise in your salary, let's say by 50,000 or 1 lakh per annum? Also, it looks like your credit score is low. Why don't you with discipline, pay the next 6 months your credit card bill without missing the deadline? That way, you can increase your credit score. That way, you have better chance of getting the loan. Not just simply deny, but providing a recourse. What can be done according to the model, what can be done to get the loan sanctioned. Okay, so in this case, it is not only explaining, but also providing recourse, what can be done in order to get the desired output. What is the desired output? Getting the loan sanctioned. Okay, so this also is a wonderful use case for having explainability in artificial intelligence. Okay, finally, one last application. Let's say you again developed a simple algorithm which is a decision tree. Okay, based on the data collected from the patients in a hospital, you developed a binary classifier which kind of takes in all these features and predicts whether the person is going to be sick or not sick. And after all the training is over, you looked at the model. The model says this is the algorithm. If the gender is female, go to the ID number, check if the ID number is 200 or greater than 200, then predict sick. And if the gender is male, also if there is cold and cough, then predict sick. Now, do you think this is a good model?
No.
Why not?
No.
Again, it is predicting sickness based on kind of irrelevant features like, say, gender, and then even the ID number. In case of male only, probably it is just looking at cold and cough only. But in case of females, it is totally irrelevant.
Correct, correct. Absolutely, absolutely right. See, when you compose data, there is all sort of information. The serial number, ID number, all sort of things are fed into the model without a proper pre-processing and cleaning of the data. Sometimes it happens, maybe the volume of the data, maybe you didn't think that this is going to be an issue. So you use the data at your hand, and after you understand the model, you think that, okay, in case of females, everybody whose ID number is greater than 200 and a female, their label is sick in the ground truth, in the training data. So the model looked at it and simply understood, okay, whenever there is ID number greater than 200, I feel I should predict sick. It is not right the way to understand whether the person is going to be sick or not. But on the other hand, in case of male data, it is doing reasonable job because it is looking for the symptoms cold and cough. So you might have invested a lot of time and effort in developing AI/ML model. You don't need to completely throw it away. At least in partial scenarios, for example, this model can be used without a problem for male patients, but definitely you cannot use this model for female because it is not reasonable to say whether the person is going to be sick based on the ID number. Okay, so this explanation helped us when to use the model, when not to use the model. You don't need to completely throw it away because industry organizations spend millions and millions on training a model. There may be some scenarios where they cannot be used, but there may be other scenarios where they can still be used. Okay, because they invested a lot. Okay, so this is also another use case where explainability helps with when and when not to use. Okay, when to use and when not to use. Okay, all right. So there are a lot of such use cases why one should have explainable AI. Okay, in short, explainability is required for developers because when they develop, they need to understand whether the models suffer any bugs, whether they suffer any bias, whether they suffer any favoritism. See, as a regulator, the government and other agencies have to understand a model before they approve, right? Given that more and more critical applications are driven by AI, like banking, healthcare, what can be more critical than banking and healthcare, right? So all these critical applications, when they are deploying AI, the regulators proactively should see whether these models suffer any bias, whether these models are discriminatory towards any gender, any race, any geographical area. All of that should be done carefully. That is why we need explanations. Also, as an end user, we need, whenever our application gets rejected, whenever we get a decision which is given, provided by AI, we need the justification why we received whatever we received. Okay, so every stakeholder in this ecosystem, starting from developers, the government, and regulatory agencies, the end users, everybody benefits from explainability. Okay, so that is why with more and more AI/ML prominence, there is more and more emphasis on explainability and explanations. Okay, and there is a clear evidence. If you go to Google Trends, in the last 5 years, from 2019 to 2024, explainability has attracted, gravitated more and more attention, more and more importance. Okay, and we started offering an explainability course at IIT Hyderabad for the last 3 years. Okay, and I mean, I hope I am successfully convinced. I successfully convinced all of you about the importance of explanations, because accuracy alone may not be sufficient. When you train an AI/ML model, so far what we have done is you tested on a held out set, and when it performs decently, you said you're happy, but no more the case. Okay, the test accuracy alone is not good enough. All these auxiliary criteria about safety, fairness, and right to explanations need to be considered. Okay, whenever.
Sorry to disturb you, sir.
Yes, please.
So what did you say about explainability at IIT Hyderabad? I missed that. Could you?
Okay, we started offering a 3 credit course for our MTech, BTech, PhD students, which was, to the best of my knowledge, not many universities offer it. Okay, we designed a course in the curriculum for the people, for the students to understand the importance of explainability. Okay, I emphasize that we have a course running. That's it. Yeah.
Okay, thanks.
And in fact, these are the slides from that course of mine. 2024, I offered this course. I am reusing some of the slides from there. All right. So again, there is emphasis on explainability. There are nations that made laws. Whenever a company uses AI to make decisions, the users have right for explanation. You can't simply take the AI algorithm and take the decisions, but not provide explanations. Okay, the user has a right to know the explanation, and soon India will also adapt. Okay, now, so we said explainability is important and all that. Now let's try to get formal look at what is explainability. And there is this another word, interpretability. People use it interchangeably, but the research community differentiates both of them, explainability and interpretability. I'll come to that. For the next 2 to 3 minutes, we'll not differentiate what is explainability, what is interpretability. But when the slide comes, I'll tell you at a research level, what is the difference? Okay, so how do we define? It's not easy to define mathematically, but how do we actually verbally define it? Interpretability is the degree to which a human can understand the cause of a decision. Okay, so there are a lot of definitions by different researchers. I only picked up some of them. I don't want to spend a lot of time on that, but I want you to understand how to go about defining interpretability or explainability. Okay, if an algorithm is very easy for a human to understand, okay, in the sense that can understand the cause of a decision. For example, all these example applications that I have shown, in all these applications, end user is the human, and the attempt was to understand what is the cause of a decision. For example, the very first question about the fraudulent transaction was about understanding the cause, why the algorithm or why a human thinks it is a fraudulent transaction, or why it is not a fraudulent transaction. If a model is easy for understanding this, then we say it is very interpretable. On the other hand, if the model is not very easy to understand the cause of a decision, and it is just acting as a black box without revealing the reason behind the decision, then we say this is not very interpretable, this is not very explainable. Okay, in short, it is the degree to which a human can understand the cause of the model's decision. Okay, and a lot of such definitions are there. It's not very important. Also, in the interest of time, I'll simply say there are a lot of different but related notions. Okay, but overall, If we can understand the reason behind the decision, it is more interpretable. If not, it is not very interpretable. Okay, the model may be very wrong. As long as it is giving an explanation, it is very interpretable. Please be careful. There may be very useless models that are explainable. Okay, we want both. We want the model to be accurate as much as possible, but at the same time, we want the model to be interpretable also. We want to be able to understand the reason behind the decision. Okay. Again, there are a lot of complications. What is a better explanation? Okay, if there are two explanations, how can we compare those explanations? This is all research, not very much figured out. A lot of research is happening actively in this area, but I want you to know that there are some interesting questions. If at all there are research students in the audience, this is a wonderful area to plan your research in the next 5 to 10 years. Okay, all right, let's quickly go and see what can be an explanation. See, there is an AI model. There is somebody. It can be a developer. It can be an end user. It can be a government agency that wants to understand and approve the deployment of this AI algorithm. Now, what is an explanation? Explanation can be or should be faithful, because the explanation should be faithful to the AI model. See, AI model doing one thing and the explanation reporting something else. We don't want that. The explanation should be faithful. That means whatever AI model is doing, the explanation should bring out accurately. Okay, the explanation cannot misinterpret the reasons behind. Okay, whatever is AI model doing, that is exactly what the explanation should be. At the same time, the explanation should be understandable. Okay, understandable easily by the end user. If it is very difficult, we are not going to serve anybody with that, right? If it is understandable only, we can serve it to whatever is the agency. It can be end user, it can be developer, it can be government agency, whoever it is. Okay, these are the primary goals. The explanation should be faithful to the model. Explanation should be understandable for the end user. All right, there are a lot of explanations possible. The model parameters themselves can act as an explanation. The example predictions can also act as an explanation. Okay, so let's take one at a time. Okay, so I know this may be a little boring, but I want you to do this exercise with me. Can somebody identify a model whose parameters themselves can act as an explanation? You might have come across a lot of AML models, right? Linear regression, logistic regression, decision trees, MLP, CNNs, transformers, whatnot. Okay, where in those spectrum of models, when I say the model parameters, that itself is a very good explanation of what is model doing. Can you identify such models?
The model which predicts weather.
So what is that model? Is it a neural network? Is it a linear regression
RNN.
model? RNN. The model RNN may have hundreds and hundreds of parameters. I will tell the values of those parameters. Will you be able to understand how the model is taking a decision? Some of the RNN models may have thousands of parameters also. I'll give all the printed values of those model parameters. Will you be able to understand how the model is taking the decision?
Okay, not actually with the use of weights and biases. No.
Correct. Can you think of other models where this may be possible?
So probably in the case of regression models.
Excellent. Excellent.
Sir, in linear regression models.
Excellent. Yes, linear regression definitely is one model. When I say the parameters of the model, you will be able to understand what is happening. For example, so don't think these are some random, this is from previous lectures. Are you able to see the notebook?
Yes, yes.
Okay. Why am I not able to? Oh, sorry. Right. Draw. Okay. For some reason I'm not able to draw. Text mode. So I want to show how the parameters act as explanation. Okay, let's take a simple model where the model is performing linear regression. The input is you're predicting, the output is you're predicting the price of a flat. Okay, what will be the price of a flat? What will be the input? Can somebody tell me what is a reasonable input for this model that predicts the price of a flat?
These area in square feet, number of bedrooms,
Perfect.
kitchen.
Perfect. Let's say this is the number of bedrooms, this is the area of the flat, and this is distance to the airport. Let's say this is how many schools are there within 2 kilometer radius, all of that. Okay, so beta 0, beta 1, beta 2, beta 3, beta 4, these are the parameters of the model. Okay, so if I say what is beta 0 value, what is beta 2 value, beta 3 value, and so on, now you understand, okay, the emphasis on number of bedrooms, emphasis on the distance to airport, okay, emphasis on how many schools are there nearby. You understand, okay, because the input, whatever is you are providing, x1, x2, x3, x4, this is the input. Okay, because the input is this way, let's say it is really far off from airport, obviously the price is going to be slightly lesser. If it is far away from schools, another reason why the model predicts less. Okay, in this model, which is a linear regression model, the parameters themselves can explain how the model is predicting, why the model is predicting what it is predicting. Okay, so simply the parameters in this case act as explanation for the model. And also, you know, if I change this particular feature by 1, how much y changes? It changes by beta 1, keeping all the other input same, only this feature is changed by 1, so the y changes by beta 1. Same, if I change the second feature by 1, whatever it is, the output changes by beta 2, keeping other things constant. So you know very well about the model, how the input is affecting the output, what are the important features considered by the model, all of that. So in this case, the parameters act as explanation. But think of a very complex neural network with thousands and thousands of parameters. If I throw all these parameters at you, you don't know how to understand these parameters. But in certain other models, the parameters act as an explanation. Another explanation can be example predictions. Let's say I give you an input, which is a X-ray image, and there is a AI algorithm which is classifying this as tumor or not tumor. And let's say this predicted tumor, and the AI, the medical expert will ask why, and it will bring out 10 such training data, very similar to the testing data, this particular one, X test. Okay, it brings out 4 or 5 samples that are very relevant to this particular test case, and say, see, I find this test input is very similar to this training data. That is the and all these training data are labeled as tumor, tumor, tumor. That is why I believe this also is a tumor. Okay, what is the explanation? Example samples from the training data. Okay, so this is one way to explain why the model predicted what it predicted. Okay, in complex neural networks and all, this is possible. These are called example as an explanation. Okay, or sometimes it is called templates or exemplaries also. Okay, in short, the model is providing example samples which are labeled similarly. Now, after looking at these samples, oh, okay, these are all labeled according to the ground truth. This also is very similar to them, so it has to be labeled accordingly. Okay, another way is to summarize the algorithm, the AI, complex AI algorithm, the black box algorithm, with a simple program or a tree. Remember that final example where female and male, the decision tree was created based on what are the symptoms and all? That by the nature is an explainable AI algorithm. Okay, remember, it just checks whether the person suffers from these symptoms. If yes, then it predicts sick. Otherwise, no. And I'm sure you might have gone through the decision tree algorithm. It will check the value of the features, some of the features, and based on the value they assume, it will predict whatever is the label. Okay, so the algorithm itself is an explanation. By the nature of the algorithm, it is very explainable. Okay, or you can create a summary like that for a complex algorithm. Let's say this model is a very complex AI algorithm, like a neural network or a random forest or things like that. Now, you provide an explanation which is just a program, a line of uh, uh, multiple lines of readable language. Okay, so this is an explanation for this black box model. Okay, how to get there? I will come and talk to you about how to get this a black box approximated as this simple linear model or a decision tree. Okay, this is an explanation for the black box model. Okay, because people can read, people can appreciate what features are involved. This is an explanation. But here, there is no such thing. Take input, predict output. Okay, so in some cases, this is also is a reasonable explanation. And so most important features, remember the dog versus wolf. This is exactly what happened. The explanation highlighted important features.
Sir,
Because,
excuse me.
please.
Can you reiterate the last point? It is not clear. Like in case of that tumor or not tumor. So what is another alternative way to
Right.
produce an explanation?
Let's say there is an input, whatever it is taking an input and giving an output. This is a very complex AI model. Okay, you don't know what is happening. You can think of it as a deep neural network taking multiple, layer after layer, non-linearity and all. Let's say I created an explanation for this model wherein it looks like if there is a circular object present, then predict tumor. Okay, I'm just writing a very simple, almost stupid explanation. Okay, think of some reasonable set of rules that approximate the behavior of this complex model. Okay, I'm not telling how I'm getting this. Okay, there are algorithms to bring this output for black box models. Okay, think of such an explanation where you are getting a readable explanation. This qualifies to be an explanation because it is easy to understand, and it is also believe that it is accurately or faithfully representing the model behavior. Okay, that again is a challenge. I'm not saying how easy or how difficult to get such an explanation, but think, let's say there is such an explanation. This is also qualifies to be a very good explanation. Okay, the explanation can be a set of rules like a program. If you find this, predict this. Else, you find something else, then predict no tumor. Okay, I'm just giving you an example.
Sure. Okay.
Okay,
Thank you.
explanation can be a summary in a program style or a rule set of rules style. Okay, that can also be an explanation because it is easy to understand. That is it. Okay, another way to explain is by highlighting the important features. For example, that wolf versus dog, if you see, it highlighted important regions in the input, important features in the input. Unfortunately, that algorithm was performing poorly, but thanks to the explanation, which is highlighting the important features in the input. That is also an explanation why the model predicted what it predicted. Okay, in vision applications, this comes very, very handy. By highlighting the important regions, I'm going to show you some examples of that kind. Okay, you will appreciate, oh, okay, because you saw these wings, you are saying the object is a bird. Oh, okay, you saw the presence of fur, you believe this is a cat. Okay, by highlighting those regions, those pixels in the input. Okay, that is a wonderful explanation for computer vision applications. Okay, and so many such things. For example, if you show that flipping, changing something in the input will flip. Okay, let's say you removed some feature here. Let's say you made x2 to be 0, then suddenly the classification label changes. So that is one way to explain why the model predicted what it predicted. These are called counterfactuals. For example, remember that banking application, you replace your annual salary by let's say in place of 1 lakh you put 2 lakh. Suddenly the decision of the model goes from rejection to acceptance. So that is also one way to explain. Okay, if I change my annual salary from 10 lakhs to 15 lakhs, the decision is positive. That means the model wants more annual salary for me to get the loan. Okay, that also is an explanation. It's a very indirect explanation. Let's say I change the current credit score from 560 to 630. Then suddenly the output changes to positive. Then you say, okay, there is enough emphasis on the model, on the credit score, and looks like I have poor credit score. That is why my loan got rejected. Okay, so you describe how to flip the output of the model. That also is an explanation, because it is conveying the message, conveying the knowledge. Okay, in any way. Okay, directly or indirectly, it is helping us to understand how the model is predicting. So this is a broad definition for an explanation. It can be any of this. It can be outside of this also, as long as it is helping us to understand how the model works, how the model predicts. That is the idea. Am I audible to everybody?
So you're audible, but
Yes.
your screen
Yes,
is
sir.
not visible.
Okay, there was some error.
Yeah, you were not audible, sir, for the past 1 minute, I would say.
Oh, I see. Can somebody highlight a point where you lost me?
When you just said that any of these five or any other
Right.
way can work as a valid explanation.
Excellent. Thank you. So any of them, see, the purpose is simple. You have to explain the model to the end user. Also, the explanation needs to be faithful to the model. Then any of these possibilities can be an explanation, as long as you're serving the understanding of the model and being truthful to the model. Okay. So just to summarize, there is enough emphasis on AI/ML utility, AI/ML applications, deployment, but we need to be very clear about how the model is predicting, because it may be a buggy model, it may be a discriminative model, because all sort of things can happen. Unless you understand that the model is bug free, the model is bias free, you cannot deploy it. Okay, so far that is the story. Lot of critical applications get benefited if we have explanations. Okay, any questions so far?
No, sir.
Wonderful. So there is one subtle aspect. There is this word interpretability and explainability. So what is interpretability? There is a slight difference between both of them. Interpretability means the ability to determine the cause and effect from a machine learning model that you trained on your data. Okay, the key here is that cause and effect. Okay, if you don't exercise, if you eat junk, you are prone to get heart attack. That is interpretability. There is a cause and effect. What is the cause? You're not exercising enough, you're not eating healthy, your lifestyle is sedate. So that is the reason why the model predicts you're prone to some disease. That is the interpretation of the model. Now coming to the explainability, explainability deals with the knowledge of what each node in the model is responsible for. Okay, what is learned in this module? Let's say you're talking about a neural network. What is learned in the first layer, second layer, how the model is putting all these features together to get the inference. If you ask those questions about the modules of the model, their interaction among themselves, that is the explainability part. Okay. In simple terms, it is the knowledge of both what a node represents and its importance towards the bigger picture, which is the model's performance. Okay. I can ask you, if you are aware of, let's say, residual networks, what is the role of the shortcut, the residual connection that is there? That is explainability. Yes, please. There is a hand raised.
Just wanted could you explain it, in more general terms, because he says what a node represents.
Yeah, node can be anything. For example, I'm talking about the beta 1, beta 2, beta 3, those parameters. You can ask what beta 1 emphasizes. I can say it gives the importance to the distance to nearby schools. Okay, that is the node. Can be anything, the parameter or a block or a layer, anything. It depends on the model. Some models have simple parameters, some models have transformations, all of that, right? Node means the constituent parts of the model. It can be anything. It can be, as I said, the one parameter, bunch of parameters, layer, or set of layers also. Okay, you can understand the model at any granularity, right? Is this clear?
Yeah, yes.
Okay, so you are worried about the internal nodes and as what they are learning, how they are helping the model to understand or solve the problem. Okay, but on the other hand, interpretability is, what is the story? You don't tell me what each of these are learning. You tell me the story. I told you the story, right? In the problem of heart attack prediction, what is the story? If your lifestyle is healthy, if you are exercising, eating healthy, yes, you are less prone. That is the story. I'm not telling you what each parameter is responsible, how they are figuring out. I don't care. You just tell me the story. What is the cause? What is the effect? That is interpretability. Okay, but if you are a developer, you want to understand what each node or a module in the model is doing, how it is putting all of these simple modules together so that the inference is made. Okay, slowly you will graduate to very sophisticated neural networks that have billions and billions of parameters. So you need to understand at a modular level, layer level, or a bunch of layers together. Okay, you want to understand how these components, you think of a car has so many sophisticated systems, right? So all of them put together will make a car, but you want to understand each of them separately. That is explainability. Okay, is this clear? What is the difference? But if you want to broadly understand, you can use them interchangeably, but I want you to be aware of the subtle difference between interpretability and explainability. This is typically at a research level, people differentiate these two. Okay, right. So there are a lot of such use cases. In the interest of time, I will not spend a lot of time. These resources are shared with you. It's easy to read also. I will give you the link to some other resources where you can dig deeper also. Okay, all right. Fine. We understood why we need explanations. We understood some definitions. What is explanation? What is explainability, interpretability, all of that. Now, how do we achieve model understanding? Okay, so now this part, how to get this part. Okay, there is a model, there is an explanation. How do we get that? How do we get for a given model this explanation? Okay, this arrow is what we are going to focus. Again, in the interest of time, I'll give you the broad approaches, how to go about one particular approach. Lime, I will discuss in detail. Okay, now let's look at broadly achieving model understanding. You can do it in two ways. One relatively easier way is, let's build inherently interpretable models. Okay, I told you the example of predicting the price of a flat, right? Using linear model, we did connect the input to output. These are linear models. Why? Because the simple linear transformation gives you output, right? And you know how each feature is important. What is the weight given by the model to each of these features? Okay, if you can work with these models, well and good, because they are inherently interpretable. Another inherently interpretable model, can somebody give me an example? I gave one, which is linear model. Is there any other inherently explainable or interpretable model? You might have gone through a lot of machine learning models, right? Machine learning algorithms. Am I audible?
Yes,
Am I-
sir.
Okay.
Yes.
Just so just think about all the models you learned in machine learning. Which of them is inherently explainable? You should
Decision tree.
decision tree. Excellent. Decision tree. Why is it an inherently explainable model? This is how a decision tree looks like. Look at the middle part of the figure. You have a very clear tree-like structure. Okay, so you have the feature value, you compare it, you based on the value, you take left branch or right branch. It is very clear. Look at the extreme right. It is also a machine learning algorithm, which is in the form of a set of rules. These are called decision rules. Okay, look at the feature value. If they meet these constraints, you predict one value, otherwise you predict the other label. Okay, these are machine learning algorithms, but it happens that they are inherently explainable. You know what is happening also. Okay, so this, if you can do, this is good. Build inherently interpretable models for solving your task. But the catch is that these models are not sophisticated. They suffer poor accuracy. Okay, then you have to go for sophisticated models like random forest or SVMs or even further deep neural networks, all of that. They give good accuracy compared to these inherently explainable simple models. They give excellent accuracy, but they are not inherently interpretable because they have thousands and thousands of parameters, tens of layers. It is difficult for you to understand. So what you do, without compromising accuracy, you train such a complex model, then train or learn this block. Explainer. That arrow that I highlighted is this explainer block. What it will do is, it will take the complex model and produce a simple linear or a decision tree like inherently explainable model, which is approximating the sophisticated model. Okay, the approximation is not going to be really valid. It can be very local approximation, valid only at a particular neighborhood in the input. It is not valid in the entire domain. Okay, so this is what the second way is. Okay, so can somebody tell me why I'm doing this? Why I have to train a sophisticated model, then go for local explanation, which is an approximation with a simpler model?
I think, sir, you already explained it, like you said,
Mhm.
we don't want to compromise on the accuracy or sophistications.
Right.
We
Right.
train the sophisticated model, but we now want an explanation. So,
Excellent. Yeah, that is the reason. Because if you can work with and live with this accuracy, you can go for this inherently explainable model. But often the case, our data, our problem is complex. You cannot easily solve with this simple linear model or decision tree. That is why you go for this approach. You train the complex model, get the desired accuracy, then go for an explanation. Okay, I'll talk about that. So this is the spectrum. You look at the left hand graph, you want accuracy, very strong accuracy, you will compromise interpretability. Okay, if you want the x-axis to be very big, large, the y-axis you have to compromise. You have to only go for neural networks or random forest complex models. But on the other hand, if you are okay with working with less accuracy, you can go with linear regression, shallow decision trees. They have very good interpretability, but their accuracy is poor. Okay, you have to keep this in mind. Some of the models have good interpretability, but they suffer poor accuracy. On the other hand, strong accuracy comes at reduced interpretability. Okay, depending upon what you need to pick. Okay, right. So if you look at the left hand side, it's a relatively simple problem. It's even a line can separate with 90-95% accuracy. Blue on one side, red on other side. That is why you can use simple linear model here. But on the right hand side, you see very complex decision boundary. Okay, very non-linear decision boundary, blue versus red. In this case, you have to go for some complex deep neural network and ask for local explanations. Okay, is this clear? Bigger picture?
Yes, sir.
Okay. All right. So that is, in other words, if you can build an interpretable model with a satisfactory accuracy, then go for it. But often the case is, yes,
Excuse
please.
me,
Yes, please.
sir, could you explain this term post hoc?
Post hoc means after you trained, you're going for an explanation. That is why it's called post hoc. Okay, post hoc means what? You've done something and then looking for explanation. Okay, you've done the training, model training, you have the black box model, then you're trying to analyze it by that orange block, explainer block. Okay, I'll come to that block. But if you
one more question, sir, maybe
Sure.
a little digression again.
No
How
problem.
is this post hoc explanation and this whole idea, how is it different from reproducibility? There is talk of reproducibility, that we have to make our models reproducible, you know. So do you distinguish or?
Yeah, they're slightly different. Reproducibility is more on how easily you can build the same model with slight variation in the data, for example. Also, particularly in the deep learning era, there is a huge emphasis on hyperparameter tuning, hyperparameter exploration, all of that. Okay, it's slightly different. If you want to reproduce easily a particular model, you have to provide all this information. Also, you need to resort to a professional way of training the model. Okay, so reproducibility is about how to get back the same model in a different scenario of training. Okay, but on the other hand, explainer here, the post hoc explanation is not about that. It's more about, I have a black box model, very accurate, but I don't know how it is working. Can you provide explanations to that? That is where explainer comes into picture as a post hoc analysis. Okay, is this clear?
Yeah.
Right. All right, let's quickly see. So post hoc means after you have the black box sophisticated model trained, you are working on that via providing a simpler model, which as an explanation helps us understand that complex model. Okay, I'll discuss one example in the next, let's say 10-15 minutes. Okay, Lime is something we will focus how to get explanations for a sophisticated model in a post hoc manner. Okay, but as I said, look at your problem. Let's say you want to decide, you have the problem at hand. First thing you should do is go for all these simpler models. You train linear model, train shallow decision tree, see if you're happy with the accuracy. If you are happy with the accuracy, that's it. You stop there. You have a model which is explainable. Also, the accuracy is satisfactory to you. But often the case, these models cannot perform to your satisfaction. That is why you have to take the second route. Second route is go for sophisticated model, get the best accuracy you can get, then go for post hoc explanation. Okay, so whenever in future you get this dilemma, you get your goal is to train a model, keep this in mind. Work with simpler models. Look if you are happy. Otherwise, you just go for complex model and look for post hoc explanation. Okay, this is the summary. Okay, now as I said, inherently explainable models. I'm sure you might have gone through this in greater detail, but I want you to quickly take a look at them from the explainability perspective. There is a lot of optimization involved in getting these parameters learned and all. Okay, but I want you to revisit all these algorithms from the explainability perspective. Okay, let's start with linear regression. Linear regression, as the name suggests, it's a linear relation between input and output. Okay, particularly in the parameters sense. Okay, but you see this equation, beta 0 plus beta 1 x1 plus beta 2 x2 and so on. Okay, parameters are learned using a loss function. You can do it with a closed form solution or a gradient descent. You can start with random initialization and perform gradient descent, slowly improve the loss, and it will converge to the local minimum. Okay, so is it interpretable? Linear regression? Anybody? Do you think it is interpretable?
Yes, sir.
I hear only one person saying yes. The rest of them believe it is not interpretable. Why is it not interpretable? Okay, the one who said interpretable, yes. Why do you think it is interpretable?
So like we say, these betas, they are providing a measure of, what is the importance of each of the features. And so even some output, we can kind of infer
Right.
that why the output is what it is.
Excellent. That's it. You have everything about the model that is there. All the betas will tell you what is the importance on each of these features. Okay, beta 0 tells what is the inherent bias of the model to predict when all the input is 0. Okay, what is the bias? Bias means without any input, the model is already predicting something which is beta 0. And now look at beta 1 and beta 2 and so on. That will tell you what is the emphasis on each of these features. You know what is x1, you know what is x2. It can be the distance to airport, it can be the number of bedrooms, it can be the area of the flat. You know how much emphasis the model has. And any other application, it need not be this flat flat price prediction. It can be anything. Whatever is the feature, you know how much weight is given by the model. That's it. You understood everything about the model. By changing one a particular feature by one unit, you know how much the output changes, right? In place of x1, you put x1 plus 1. The rest of them is unchanged. So y changes by beta 1. Okay, so that's why we say this is inherently explainable. You know how the model is predicting, how the input can impact the output. Very clear. In and out, you know. Okay, that is why we say linear regression and logistic regression are very, very inherently explainable, because the model is very transparent. You can relate input and output via a linear equation. That's it. Now, there is another matter. What if my features are 1000? What if my features are 10,000? Yes, it slowly goes out of hands. You cannot go through all the 1,000 of them. But you know, if the number of features that you look for is a handful, these models are very interpretable. Okay, even for 10, 20 features, you can understand, okay, what is happening, how each feature is impacting the output, all that. Okay, that's why we say logistic regression and linear regression and even shallow decision trees are very, very inherently explainable. Look at this algorithm. This is decision tree output. It looks at the age. If the age is greater than 50, it looks at the BMI. If the BMI is greater than 25, it will predict, yes, this person is prone to a stroke. If the BMI is less than 25, then it says, no, the person is not prone to stroke. Okay, similarly for the other branch. So the algorithm inherently is explaining how it is working, why it is predicting, what it is predicting. Okay, so because look at the second thing, second branch, HD, hypertension. If the person is suffering from hypertension, it is predicting stroke. It is reasonable to understand. Okay, so this is why I say decision trees, the two shallow decision trees. Again, if you have a decision tree with 1,000 depth, it's impossible for us to quickly understand and easily understand what is happening, right? That's why particularly you restrict the depth of the decision tree so that it is humanly possible to understand. Okay, humanly possible, average person, how easy it is for the average person to understand by looking at it, by going through it. Okay, so that is why we say these models are inherently explainable. Okay, so any questions on inherently explainable things? Because we want to go look at one of the algorithms in the post hoc scenario, because this is more practical. Because as I said, these simple algorithms compromise a good amount of accuracy. In the end, even if it is explainable, if it is not accurate, you don't want to use it, right? You want both accuracy and explanations. That is why you typically go for post hoc explanations. So let's take a quick 1 minute pause. If you have any questions, please bring them on. Okay, so let's look at the post hoc explanations. Hold on, I'll use another slide deck. Is the new slides visible?
Yes, sir.
Yes, sir, they are visible.
All right, thank you. So let's look at one example for the post hoc explanations. Okay, so particularly these post hoc explanations can be model agnostic. What do we mean by that? It doesn't matter what is your model. Okay, it can be a deep neural network. Within deep neural networks also, it can be anything: MLP, CNN, or RNN, or vision transformer, a combination of them, or a random forest, anything. Okay, SVM, it doesn't matter. You can use this model agnostic in a model agnostic way. It doesn't matter what is the model. It is simply a black box. They will provide you a simple explanation, local explanation or a global explanation. What is local? When you provide explanation within the context of one data sample. For example, look at what we started with, that coffee shop transaction example. I want explanation for the model within that sample neighborhood. Okay, what is the sample here? That sample is, so in that case, let me just take 1 minute. So in that example, what is my input X? Can somebody tell me what is the possible input for that fraudulent transaction AI algorithm? What can go as input to the algorithm? The goal is to predict fraudulent or not fraudulent. Okay, you can call it genuine. Now think about and let me know what features make sense as input to this algorithm.
The
Amount, excellent. Amount of the transaction and
Time.
sorry,
Time at which the transaction is made.
time of excellent. Time of transaction. Location or geography, correct. And so many other things. Okay, whether this person, how frequently the transactions happen and all that, so many other features. Okay, so this is 1 point x1. Okay, I said 10,000, 3 a.m. in somewhere in Hyderabad. Okay, all of this becomes one sample, x1. Okay, x is the multi vector feature. Okay, now I can provide the explanation for the model within the neighborhood of this x. Okay, this x can be a high dimensional point, 1 point in the high dimensional input space. Within the neighborhood of that point, very close neighborhood of that point, I am providing explanation for this. Okay, the explanation can be a simple linear model. I can approximate this black box model with a simple linear model within this neighborhood. Okay, this approximation is valid only within this neighborhood. And if you move away from this, the explanation can be wrong. The approximation can be wrong because we are approximating within the neighborhood, close neighborhood of this 1 point. That is why it is called local explanation. But on the other hand, you can try for a global approximation of the model. Then we can call it global explanation. Okay, but those are prone to errors. it is impossible for us to approximate a complex model with a linear model everywhere. Because if that was possible, we would have gone for linear model in the first place, right? Because the linear model wasn't performing well, we went for sophisticated model. So you cannot approximate globally, but it may be possible for you to approximate locally with a linear model or a simple decision tree. It may be possible locally. Okay, is this clear? Why I'm saying locally? Because this is a complex model. It will have a very non-linear classification boundary. So within the neighborhood of a point, yes, you can approximate with a line. But if you use this line everywhere, this is going to be erroneous. Okay, that's why when you do these post hoc explanations, you typically do it for local approximation, local explanations. Okay, but global is also possible, but it's really challenging to get accurate approximation. Okay, just 1 second. Somebody is calling me persistently. I'll find out. Sorry, I'm sorry about that disturbance. Okay, so let's look at how the local explanations you can get in a post hoc sense. Okay, so local explanation can be anything. Again, you saw how or what are possible explanations. It can be feature importance. It can be a counterfactual. Counterfactual means flipping some of these inputs can change the output of the model, right? That loan application, by increasing the annual salary, by increasing the credit score, the loan decision can be changed, right? Saliency maps is that dog and wolf algorithm, dog and wolf classification algorithm, where it highlighted the salient parts, the important parts of the input. Okay, prototype based means giving examples. From the training data, the explanation can bring a set of examples that can help us understand why the model predicted yes or no. Okay, by throwing some examples at us, it can explain. It can be anything. It is just that local explanation. This explanation is valid within the neighborhood of this data point. There can be completely different explanation. For example, the time, right? Somebody pointed out that it's a fraudulent, it looks like a fraudulent detection, fraudulent transaction because the time was suspicious. Okay, within this time ranges, you have to have a different model. Let's say if it is the regular daytime like 10 a.m., 11 a.m., you may not feel it is it is less likely to be fraudulent. Also the amount, if somebody said only 500 rupees, you don't worry much about, because based on the transaction amount also the approximations, the explanations change. Okay, so you need to have any one of them. It can be an explanation for the model. Okay, now let's look at one particular example. So by the end of this module, you will be able to appreciate this algorithm that I'm going to describe. It's called local interpretable model agnostic explanation. See, it has more phrases, but it is very simple. It is local. That means the explanation is valid only within the neighborhood of that point. And interpretable, because we are using an interpretable approximation. It can be linear model, it can be decision tree, which will approximate the black box model within the neighborhood of that local. And also model agnostic. Why do we say this algorithm is model agnostic? It doesn't matter what is your sophisticated algorithm. I don't want internals about that algorithm. I want it as a black box, input and output. So any algorithm you have can be explained using line. That is why it is model agnostic. Okay. Is the name clear? Why it has a long name? It's a local approximation. So the explanation is going to be valid only within the neighborhood. Okay, let's say the betas you have are valid only within the neighborhood of that example point you have. Okay, the test sample you have. All right. Now, the goal here is to identify an interpretable model, either a shallow decision tree or a local linear model, and over the interpretable representation. Okay, that is very important. See, the explanation should be very easy to understand. That is inherently there. You have to convey in a language, the explanation should be so easy to understand. It can't be complex for the end user to understand. Okay, let's look at an example that will tell you a lot more than these slides. Okay, let's say you have a sentiment classification algorithm. You built, you want to buy some products from the e-commerce websites like Amazon or Flipkart. Okay, people who purchase those items leave some reviews, some comments. Let's say one book you wanted to buy, there is a review like this. Somebody wrote, amazing book, especially few examples can make the essay praiseworthy. So do you think this is a positive sentiment about the book or not? Am I connected? Are you able to hear
Yes,
me?
sir. Yes,
Okay.
sir.
So if you see this kind of a review, what do you think? It is a positive review or a negative review?
Positive.
Why do you think it is a positive?
Because of the adjectives, positive adjectives that
Excellent. Right. That's as simple as that. Because we are intelligent enough, we can classify it correctly. Also, we are explainable enough. We are explaining why we believe it is a positive. Absolutely correct. The words like amazing, praiseworthy clearly tell us that it is a very positive sentiment that is expressed in this review. Okay, let's say you built an AI machine learning algorithm that classifies this into positive, negative, neutral. Three classes are there, three-way classification. Okay, see, for any machine learning model, input is a vector or a tensor, more generally tensor. It can be a multi-dimensional array also. Okay, now what happens? The input we see is a text, but the input machine learning model sees is a feature vector or a feature tensor. The interpretations or the explanations should talk the easy language for us to understand. What I mean by that is, let's say the input can be represented like a BOW representation, bag of words representation. Okay, so okay, some of you may not be aware of bag of words representation. What it means is that bag of words representation counts the occurrences of each word in the dictionary in this sentence. Okay, so wherever there is amazing, you count one because there is one instance of amazing. Book also occurred once, easy occurred once, etc. If there are multiple occurrences of the same word, the count for that will be as many times it occurred. So essentially, you are representing the text as the number of counts. Just 1 second. Sorry about, there is a visitor for signature. Just 1 second. Sorry again. Yeah, so what I mean by that is bag of words representation is very easy to understand. How? See, this is my dictionary. Okay, dictionary will have all words from A and all the way to Z, zebra. Let's say zebra is the last word. It will have hundreds, maybe thousands of words. Okay, let's say there is the text. The book is amazing. Okay, I want to represent this text as a vector. How do I do that? I'll see how many A's are there, none. How many An's are there, none. How many E's are there, one. Book, there is one book. Okay, like this is a histogram of the words essentially. Okay, is it clear what is bag of words representation? Is this clear?
Yes, sir.
Okay, so I am converting the input into this form. Why do I do that? Because I know I can easily interpret, I can understand this better than the feature vector. The feature vector can be, I'm not sure if you are aware of, it can be word to vec. Okay, it can be glove. Lot of text embedding representations are there. Text embeddings, these are called text embeddings. What they do is that they take a text and give a vector. The vector can be dense vector, real values will be there. But here BOW, it's long vector, no doubt about it. It's very inefficient, but it is easy to interpret. Why do I say it is easy to interpret? You know how many A's are there, how many An's are there, how many N's are there, all of that. But here you don't know that. There is no meaning associated with each of these components also. Okay, that's why we want some representation like this to be able to appreciate which words are important, which words played crucial role in the decision of the model, all of them. Okay, so please stop me in case you are not following. I'll finish off the application first, then you will appreciate it better. Despite that, if you have any questions, please feel free to ask questions. Okay, first let us complete the argument, then you will be able to completely understand. Okay, so the AI model we have is a simple text classification. Input is a text. It can be one line, it can be paragraph. Then the output is one of the three classes: positive, neutral, negative. Okay, now what I'll do is I'll construct this bag of words representation. Remember, the model is trained. You have decent accuracy. Okay, now we are analyzing post hoc. Okay, so please remember, somebody has trained the model, or you yourself have trained the model. Now you want explanations for the model. Okay, now what I'm going to do is that for all the input, I can provide this X prime representation. X prime representation is a simple BOW representation. Okay, so what Lime does is, this is the model you are approximating. If the input is RD, D-dimensional input, to R can be +1, 0, -1. Okay, three classes. Explanation you are providing via a simple linear model. Okay, G is the family, capital G is the family of linear models, linear or logistic regression, because it is a classification. You can think of it as a logistic regression, where it's a simple linear model that will pass through the sigmoid neuron, sigmoid activation, sorry, not neuron. Okay, so this is it can be, again, remember, one of the possibilities is linear, another possibility is shallow decision trees. Okay, that is also inherently explainable. I want to approximate the black box model F with a simple linear model G. Okay, how am I going to do that? I'll show you. And also we need another proximity measure. Proximity measure means it tells you how far a sample Z is from X. Think of it as a distance measure between Z and X. Okay, I have X. I am looking for samples that are close by to X. Okay, if the Z is close by, it will have smaller distance. The measure, I mean to say the measure phi X of Z will be smaller. If the sample is far off, the measure phi X of Z will be larger. For all practical purposes, you think of as a distance. Okay, distance between Z and X. And faithfulness of Z also should be there. We need to provide a reasonable or close approximation to F with G. Okay, that is why we compare F and G within the phi neighborhood. Okay, so this final sentence is to approximate F very closely with G. Okay, see, without a measure, we cannot say how close my G is to F, right? So unless we ensure the approximation is very, very acceptable to F, we cannot use this as an explanation. Okay. So how do we learn the G? This is how we learn the G. Okay. We want that argument G, which minimizes the loss or comparison loss between f and g within the neighborhood of x. Okay, phi x is the neighborhood. Let me draw it for you. So let's say if my x is a two-dimensional point, it will have two components x1 and x2. This is my x. Okay, this is vector with two components x1 and x2. So within this neighborhood, I want to approximate f with g. F is the black box model, g is the simple linear model. Okay, whatever f does within the neighborhood, the g also does the same thing. Remember, ours is a text classification. Okay, whatever the labels are predicted within the neighborhood of this point x, neighborhood means all these points very close by to the x. The same decisions have to be given by g also. Okay, you take whatever point within the neighborhood, whatever f predicts, g also should predict the same thing. That is how I approximate f with g within the neighborhood. Okay, that is what the loss L is doing between f, g, and phi x. Phi x is just to understand what is the neighborhood of. Okay, x.
So this Z is the input to G, right?
Z is basically here. Z in this case is basically comparing 2 points x and z. Okay, in this equation there is no z, but here phi x of z is basically, I'll show the equation for phi. That will be very clear. Let me show the equation for phi. Where is this? Here. You see the second equation. It's a simple distance measure exponentiated. Okay, it can be L2 distance between D. Capital D here is the L2 distance. Okay, if the distance is smaller, the phi will be given more importance, because you don't want approximation very far off. Okay, you don't want approximation to be close very far off. Within the neighborhood, very close by, the approximation should hold. You don't worry if the approximation doesn't hold far off. Okay, is this clear?
Yeah.
Okay, so let me.
So the sigma was variance, right?
No, sigma is okay. In this case, sigma is a constant. You can think of it as a variance, but it's a simple constant. Yeah. Hyperparameter. Yeah. I'll come to that. Okay, I'm jumping forward. Let me just go slowly, because this is something you will implement in the afternoon session. Okay. Again, we will go through it again. Let me just go complete the algorithm, and we will discuss it in case you have any doubts. Okay. The whole point is, I am approximating f, which is a black box complex model, with g, which is a very simple linear model. I cannot approximate at all points. I am only approximating locally at 1x. Okay, so that is why, how do I do that? This last function, I'll come to that. The last function we are using here, L, ensures faithfulness of g. Okay, whatever f does, g also tries to do the same thing. That is how we say g is faithful to f. Okay, so how do we do that? This is how we do that. So we compute this loss and minimize this loss while finding the g. Okay, g is the local approximation for f. Okay, so there is a regularizer. Regularizer is to ensure that you are not overfitting. Okay, regularizer can be, in case of linear regression, try to reduce the number of features you are using. Okay, remember lasso regression, where we do L1 regularization or L2 regularization. Okay, so plus lambda times whatever is the last function, you add this regularizer. Okay, that's called lasso. Basically, that is what we are also doing here. Okay, right, now let's look at the characteristics of live. How do we learn this equation, or how do we optimize this? Okay, we need data to optimize this, right? How do we do that? We only have one point, small x. The reason we can learn is that we are generating more samples within the neighborhood of x. Okay, in order to locally approximate f with g, we need to generate samples. But all that we have is only one sample. Can somebody suggest how we can go about generating more samples?
We can model the distribution and then generate around it.
Unfortunately, that's a very good idea. But unfortunately, we have only one data point. We have no access to more data which is required for modeling the distribution of the data. That's an excellent thing, but we are restricted with only one point. Can you now think of what we can do?
So maybe add noise, randomly to that
Excellent.
point.
Yes, yes. That's the easiest thing we can do. In fact, Lime does exactly the same thing. We'll sample around that X prime. How? By adding some uniform random noise. Okay, we'll generate more nearby samples. Okay, so remember our X prime was basically the interpretable representation, the BOW representation. Okay, lot of zeros and some ones and twos were there. I can add some zeros and ones to that representation to generate more nearby samples. That way, I'll get more data to train this equation, to optimize this optimization equation, this one. Okay, my goal is to approximate F with G, but I don't have training data. Remember, I am working with only one sample where I want to approximate F with G. Okay, so that is why the algorithm suggests to sample Z prime, which are perturbations to the X prime. Okay, perturbations to the BOW that we constructed. Once you have this Z prime, you can pass through the black box algorithm to predict the label. Okay, so you can get the FZ, which is the label. Now you had lot of Zs and FZs. You can train the G. You have the data set now. You can train the surrogate model G, small g. Okay, we are augmenting, in a way, we are augmenting one data samples to say 200 points or 300 points to get the model G trained. That is how we train this model. Okay, we optimize this algorithm, equation to get the local surrogate for F. Okay, so once you get that, you have a simple linear model to explain the model F within the neighborhood of that small x. Okay, one point within the neighborhood of that point, you have an approximation to F. And good thing is that this is a simple model. Inherently, it is explainable. Okay, also when you sample, some of the points can go, this is what happens, right? This is X. When you sample, some of them will be very close, some of them can be very far also. So you give less importance to the far off augmentations, more importance to the close by ones. How do you do that? The phi will help us. Okay, phi zx. If this is more, the distance is more, the weight will be less. The distance is less, the weight will be more. Okay, that is exactly what is happening here. If you see d of x comma z, yes, please, there is a question.
So just wanted you to repeat the story after, like we generate these additional, features by adding the perturbation to the original point. What after that? Can you repeat?
Yes, I'll do that. So you had one point x. You created the BOW representation for x prime. Now you added lot of noise. Okay, you got x1 prime, x2 prime, and so on, x200 prime. Let's say I have got 200 augmentations by adding 200 different noises. Okay, now with this training data, this is only input, right? You need labels also, because you have F, the fully trained black box model is there. You pass them and get the label for each of them. Okay, so you have supervised data now, x2 prime and so on, F x200 prime. Okay, you have now a data set for training G. Okay, is this clear?
Yeah.
Because you created the data set from the augmentations, now you can train G. How is this an approximation? Because these labels are provided by F, you are just copying F. Whatever F said, you are following, the G is following. That means you are emulating, you are copying F. Okay, you are learning as if whatever F is done, my G is also doing the same thing within the neighborhood of that X. That is very important. This is within the neighborhood of X. Okay, you are training. This is a simple linear regression or logistic regression. Whatever way we train linear regression and logistic regression, use the same algorithm to train this. Okay, so that is what is happening after you, this equation means exactly what I described. Okay, you are learning a logistic regression with the augmented samples that are provided. Okay, is this clear now?
Yeah, that part is clear, sir. Can you repeat this, the role of this pi function, that how this neighborhood thing would work out in this?
Okay. So let's go there. So when you generated all these 200 samples, because you are randomly adding noise, uniform noise, some of them come closer, some of them far away. Okay, but you cannot take everybody with same importance, right? Somehow you need to weight these people less and give these people which are close by more importance. Intuitively, you want to give more importance to them, less importance to them. How do you do that? That is where this phi comes into picture. Okay, so if you see, look at this. If the distance between the two x and z is small, the phi will be high. Correct? Because it is e raised to minus d. If the distance is small, that means z is very close to x, it will have a lot of importance. That is the multiplying factor for the learning loss. You look at the third equation where the weight is multiplying directly the MSC loss. This is MSC loss. Remember, mean squared error loss. Okay. If the point Z is far, it will have less importance. So the weight in the loss minimization is also relatively less compared to the nearby point. Okay. This is a simple intuition mathematically realized with this form. I hope this is clear.
So now the Zs are basically
correct. These are my Zs. Z1, Z2, Z3, Z200. Yes.
These are Zs.
These are Zs. Sorry. Yeah. You can remove X primes. You can call them Z1, Z2, Z3, and so on. FZ2, FZ.
Right.
Whatever. Yeah.
Fine.
So yeah. So that is the way we are emphasizing some of the nearby points need to be given more importance and some of the far away points should be given less importance, because when you sample, the noise can take you anywhere. If you are sampling very small, very close by, yes, you will lie very close by, but it may be possible for you to go slightly away and that should not affect you badly. So this is extra care you are taking. Okay.
Yes.
Right. So with that, you learned the model. You learned the G, which is the linear approximation. So look at this figure. The complex model learned the very non-linear classification boundary between red and blue. Okay. So red and blue is the two classes, and F learned the very non-linear complex boundary. But here, where the plus is highlighted, that is where you want to find local explanation for that complex here. So that is my X. I generated lot of samples Z. Remember, the Z are augmentations of X. How? By adding noise to these augmentations I created. Okay, that's why see whatever points that are close to the highlighted plus, they are big in size. Big in the size means they are given more importance during the optimization. The phi value will be high for nearby points. That is why they are shown bigger. And far away points, both the circles and plus, they are given less importance. That is depicted by their size. Their size is very small as they are far away from the point we considered. Okay. So with these augmentations, I can train the dotted line you see there. That is the result. That is the line, the local approximation, linear approximation for the complex model at that point. Okay. This point, the bold plus is there, right? That is the point at which we are approximating. We are providing the explanation for the model. Okay. So this is how it can be trained. And now you see within the neighborhood, the model is almost linear. Okay, whatever you see, the separation between the red and blue nearby that point is almost a line. So it is a valid approximation. Okay, even at other locations also very close by, any nonlinear thing at a sufficiently small neighborhood, it can be approximated as a linear classification boundary. Okay, once you have G looks like this. Remember, how does G look like? So it looks like sigma beta 0 plus beta 1x, beta 2x2, and so on. Now this is inherently explainable. So whatever is the point x, at that point you see what is the importance given to all these individual components based on what is the value of beta 0, beta 1, beta 2. You understand the model. The f is understood through g. That is why it is called post hoc indirect explanation. You are understanding f, but you're looking at g to understand the f. Okay, is this clear? That is how we provide approximation but also explanation for the model, which is local, not global. Okay, local explanation.
Yes.
Okay, right. So there are multiple models. Sparse linear explanation, you can find a linear model. G is the linear model, or sometimes you can also train a decision tree also. That way also you can provide explanation for f. Okay, so again, I'm skipping some of the technical details, which is not very required at this point in time. I hope the intuition is very clear. Intuition is basically you have a very sophisticated black box model, but you are looking for a simple model that can explain. So you are training by augmenting the one sample you have. Okay, and then training the model. Once you have the model trained, the G can provide you explanations for F. Remember, it is valid only at that point. Because you are worried, you are interested to explain that sample's inference, you are constructing the model G only for explaining that sample X. Okay, for example, you see, later after some time, you have another point X2 here. You trained already G here. That G cannot be used to explain this sample. You have to freshly train another G within the neighborhood and take that G2 as an explanation for this sample. The model is same, F is same, but because the points are different, the model approximations are also different, explanations can also be different. Okay, is this clear?
Yes, sir.
Okay, all right. So let's look at one example. It's a text classification. Okay, so this I took from the paper itself, the paper that came up with this algorithm, LIME algorithm itself. They used a SVM model with an RBF kernel to train the classification. It's a binary classification. Whether an email received by a user belongs to Christianity or it is not related to Christianity. So there are two classes, Christianity versus atheism. The labels are only one of them. Okay, you have a lot of such emails collected and labeled. Okay, it is a subset of bigger data set called 20 newsgroup data set. Okay, so this is how the model is performing. Okay, so on the left hand side, you see the document from Paul D to is not there, but subject David Koresh is God something. Okay, so if this is analyzed after training, the model is predicting atheism. Okay, apparently the label is also correct. I mean, the ground truth is also atheism. It is correctly predicted. But look at the importance given to each of these words that are present. Okay, God, mean, anyone. So I hope you're able to see. So look at the words that are present. Okay, and the weight given. The longer the bar, the more is the weight. Okay, so look at the importance given. It is giving on the God and mean, anyone, and other words. Okay, on the other hand, look at the right hand side. Okay, so right hand side is another mail. Sorry, another algorithm. Sorry, my bad. Another algorithm, which is algorithm 2. The input is the same thing. I am analyzing the input through the same input through two different algorithms. Okay, but look at the explanation for the second. Second one is giving importance to posting, post, etc. Okay. Now, which algorithm do you think makes more sense?
Algorithm 2.
Why is that?
So because it is saying the explanation in the algorithm one, God has given like a more weightage, and still the predicted is atheism, means the explanation couldn't be that much correct.
Okay. On the other hand, algorithm 2 is not giving more importance to God. Instead, it is giving more importance to posting. Despite that, it is saying it is okay. Because of that, it is saying the label is atheism, right?
Yes, sir.
Okay. But on the other hand, don't you think the words related to God and Christianity should be given more importance, independent of what it is predicting? In this case, it happens that the true label is atheism. Both the algorithms are predicting the true label. It's not like one of them is correctly predicting, other is not. No, both of them are correctly predicting. But I think now you should give more importance to what features it is looking for, right? So the prediction is same for both of them, which is true. But for predicting atheism versus Christianity, the words related to God, religion, etc., should be given relatively more importance, isn't it?
Yes, sir. Algorithm 1 predicts in a better way, that is, it extracts the correct feature,
Right.
and then it has come to a conclusion. Whereas algorithm 2, the feature may not be proper.
Correct. So that is a better way to look at it, because look at the words it is giving importance to. The second algorithm, it is giving importance to general words. RE means reply. Okay, by, in, NNTP, something technical, not related to Christianity or atheism. Okay, so these words are getting relatively more importance. Okay, it is doing correct classification, no doubt about it, but somehow the explanation is not reasonable. But on the other hand, algorithm 1, it tells the words like God and not the words like at the rate, NNTP posting. See, NNTP posting host is not, this is something related to the mail, not the content of the mail. Look at this. This algorithm is giving importance to NNTP, RE means the reply respondent or something like that, right? So those are not the right words to emphasize when you classify. Instead, you look at the content, look at the body of the email. Subject also is very important. Okay, so that is how the algorithm comes up with. Lime comes up with an explanation for the SVM. Okay, so now you know which algorithm to be picked, because you know which words are getting more importance, and you can relate whether that is convincing to give more importance or not. Okay, all right, so I'll stop here. There is a lot more content definitely possible, but let me quickly revise. Okay, I know there are a lot of things we discussed when we discussed about Lime. So let me just recap what we have done and summarize so that you can go through this algorithm in a hands-on session in the afternoon. Okay, so objective is simple. Okay, 1 second. Objective is simple. You have a black box model. It can be text classifier, it can be image classifier, anything. So you have to create an explainable or an interpretable input. Okay, this, remember, the BOW we created so that we know how much importance to each of these words can be given, right? Remember, this in the end will act as an explanation. Remember, see, let me go back again. So how did we find that importance score? From the slide, there was God, there was posting, etc. These were the weights given, right? How did we find this? Remember, our input X prime or Z was a BOW representation. What is a BOW representation? You know, it will have as many components as the number of words in the dictionary. Okay, it's a long vector. Okay, So position 1 is A, position 2 is an, and so on. Last position will be Z or zebra, last word with Z. Okay, now beta 1, beta 2, and so on, beta, let's say 10,000. Okay, so this is the model we learned. The G approximating the F looks like this. Okay, that is where the weights are displayed. What are the top weights given by G? Okay, the top weights given by G are shown in this slide. So that is how we are convinced one of the algorithms is better than the other. How? Because we learned the betas for all the words in the dictionary. Okay, so our feature vector now is BOW representation, which is as long as the number of words in the dictionary itself. So you know, if I change the words, the inference is going to be different, because it is going to be this beta I xi, sorry, beta I xi, I runs from 1 to 10,000 if 10,000 is the number of words in the dictionary. Okay, so the original SVM might have used, let's say SVM is the complex algorithm we trained, and this is my F. I am approximating this with G, which is the logistic regression, binary classification, logistic regression. Okay, so this is using BOW representation. I'm calling this X prime representation. This can use X. X can be word to vec or any other word embedding. Okay, sentence embedding measures. It doesn't matter. G approximated F within the neighborhood of 1x, and it has given us an explainable, inherently interpretable model. The betas will help. What I displayed here is the betas. Remember, the more the bar, the weight is more. Okay, so is this clear?
Sir, this last slide, this current slide, this part I actually missed. I had to get up.
Okay, so basically after training the G, I am displaying the top weights, the betas. Out of all the 10,000 betas, I am assuming 10,000 is the number of words in the dictionary. Out of all those 10,000, what are the strongest betas? And which words assumed that strong betas? Okay, so these are words, right? A, and B, and so on, all the way to Z, right? So beta 1 for A, beta 2 for A, and so on. You can understand, you can relate the betas for each of these words. Out of all these betas, which betas are strong? I am displaying that in this slide. Okay, left one algorithm, this is for F1, right on another algorithm F2. Okay, I didn't disclose what is my F1 and F2. Let's say I am given two algorithms F1 and F2. Now I am understanding which is better by explanations. Okay, for both I found G1 and G2. Approximating F1 is G1, approximating F2 is G2. I learned the betas for G1 and betas for G2. I displayed which betas are the strongest. And it makes sense for the algorithm 1 because the God related words are given more importance in algorithm 1. On the other hand, the important words are not related to God or religion or atheism, but on the other hand, they are related to the mail structure. Okay, that's how I deem algorithm 1 seems to be reasonable, because it is giving more importance to relative words than related words than unrelated words. Okay, so this is how you can. Sorry, is there a question again?
Yeah, so just what's the role of this bag of words? Like, see, we started with one particular review, one particular feature vector, and we created this G in the neighborhood of that.
See,
right? That particular review.
Yeah. Let me go there.
So if we change the review, then obviously we'll have a different input.
That is correct. You will get another explanation for that input. Okay, so that is where I think you might have missed what I said. So there are 2 points here. One point, you have one explanation. If you want for another input, you need to find another G. Let's say this is your another review. Okay.
Yeah, so that part I got. So coming back to that last slide you showed, so that refers to that one particular review, and I mean the approximations, both those algorithms are approximations around that particular point.
Yes, it's the same algorithm. Same data. Two algorithms, same data. Let me show.
Okay.
So remember, look at the document, the bottom part. It's the same email. I am feeding the same email to both algorithms, different algorithms.
Right. Right.
Okay. One algorithm is giving importance to God-related words. Another, the pink words highlight the important words. Okay, based on which the model is predicting the label.
Right, right. So it is like starting with that review which you said for the amazing book and praiseworthy. So that is one single review, and then we are building two different algorithms using the same data.
Yes, 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 yes.
Oh,
right.
fine.
So assume that two people came with different algorithms trained on the same data. Let's say accuracy is also very similar. Now, via explanations, you can find out which is more agreeable.
All right, all right.
Right.
Sure. Thank you.
All right. So yeah, so this is what I had for today's discussion on explainability in AI. I want you to take some time, because I'm sure the fact that you are enrolled in the summer school tells you that you are all very interested. But keep in mind, not just accurate model. Explainable model is something we want now, because algorithmic decision making is increasing. It's getting prominence every day. So we don't just need accurate models. We need explainable models that we can welcome into our lives. Okay, so I hope I have inspired you about explanations, the importance of explanations in AIML. And there is a growing literature on how we can make the models explainable, how we can work with critical applications and trust our well-being or prosperity with the AIML. Okay, thank you. Thanks for listening to me. Thanks for your 2 hours. And the contents are available online also. You can browse my website, personal website. You can get all the access to the references and all. Okay. Can we have the paper link? Yes, it is there in the slides. I provided the slides to the organizers. Even, let me just quickly check. Okay. So if you go to my personal website under the teaching, let me show it to you. So this is my, are you able to see the browser? Anybody?
Yes, sir, we can.
Yes, sir. Yes.
Okay. So if you go to my personal website, go to teaching, there is explainability in machine learning. Go there. There are resources. I'm not sure if it is accessible outside IIT Hyderabad, but materials and lectures should be. I'll look at the slides and make it available for you. Okay, so there are papers, there are links to reading material, everything. Okay, it's a full semester long course, but it is a research level course. So half the time we teach, half the time we discuss papers and projects. Okay, so it looks like a 1.5 months to 2 months course only. But remember, there is project component which is not shown on the website. Okay, feel free to go there, access them. All right. Thank you. And
Thank you so much.
at 2 o'clock, I will have my TA, Mr. Ishwar, who's working, who's having some research experience in this explainability, will handle the hands-on session. You will learn to apply line on black box classifiers. Okay, please participate and make the most of it. Thank you.
Thank you so much, sir, for the
Thank you,
wonderful
sir.
session. We really had a great time.
Thank you. Thank you. It was a pleasure. You've been a wonderful audience. Not often I get a lot of interaction and questions. It was a happy thing. Thanks.
Thank you so much, sir.
Thank you. Thank you.
Okay, now I can leave the meeting, Supriya?
Yes, sir. Yes, sir.
Thank you.